Welcome to the fifth lecture of modern construction materials. Today we are going to talk about the development of microstructure. We have already covered the bonding between different types of materials, how the structure forms, and in the last lecture we looked at the movement of atoms through diffusion, dislocation movement and so on. Now we are going to look at how the microstructure develops, and we will see what governs the microstructure formation and changes that can occur in the microstructure. Now what is the microstructure? Details of the structure of a solid that can be seen only at high magnifications, say under a microscope, are called the microstructure. Now there are different kinds of microstructures that form in materials, in solids. You can have crystallization from a melt, where you have a molten metal or molten rock that is crystallizing, solidifying, forming a crystalline solid. You can have amorphous and crystalline materials forming from precipitation from a solution or crystallization from a solution. Say in the case of hardened cement paste, you initially have a mix of cement and water, cement reacts with water, there is a precipitation of calcium silicate hydrate, which is an amorphous material. You can also have solidification without any crystallization, like in the case of glasses or thermoplastics. Silicate glass forms without crystallization through solidification. You can have limited crystallization for some plastics, that is, some plastics can have some amount of crystallinity, the rest would be amorphous. This is again something that we looked at a couple of lectures back. We can have solidification occurring from the gas phase also. For example, in the case of silica fume, carbon black, these are amorphous powders. Silica fume you would have heard of is a material that is very useful in concrete, because it has a very high silica content and it is amorphous. This makes it possible for this silica to react with calcium hydroxide, that is there, that is a byproduct of the reaction between cement and water. The calcium hydroxide reacts with the silica fume to give us a form of calcium silicate hydrate, which acts as the binding material in concrete. We also have sintering occurring. We looked at this when we looked at diffusion in the last lecture. Sintering of inorganic powders occurs in ceramics and bricks, where you have heating or partial melting. It does not, the temperature is not high enough to cause a complete melting. This gives rise to sintering between different particles, which leads to bonding of different particles and a sintered solid. So these are the different kinds of microstructures which can be formed in solids. Metals, polymers and glasses solidify from a melt. So generally when you want a solid of one of these types, you start with a melt and go on to get the body or the structure with one of these materials. Now as we saw earlier, solidification does not always involve crystallization. In metals mostly we have crystallization. We looked at an example of metal glass which is different, but in most metals we have crystallization. On the other hand, we have glasses which are most often amorphous or non-crystalline. We also looked at polymers which are generally amorphous, but you can have a solid structure which is partially crystalline due to the arrangement of the polymer chains. We discussed also in the previous lectures that most materials, most substances including metals can be forced to form a glassy structure, an amorphous structure, if the cooling rate is fast enough. that is, there is not enough time for nucleation to occur, for the arrangement of the particles to form a crystalline structure to occur. That is, if the cooling rates are fast enough, you have a higher tendency for a glassy or amorphous structure to form. However, polymers can only partially crystallize because of the nature of the long chains that make up these polymers. So, even if the cooling rates are slow enough, polymers can only crystallize partially. You remember that we looked at different type of polymers like branch polymers, linear polymers, and we said that linear polymers would have a higher tendency to crystallize, that too partially, because the chains start entangling themselves and it is difficult to have these chains align themselves in an orderly fashion. In cementitious materials, the microstructure is developed by solidification or precipitation from solution. Solutions in these cases are made up of a reactive solid and a liquid. In the case of hydrated cement paste, we start off with cement, a powder, and water. Reactions between the cement and water go on to form the hydrated cement paste. The products are generally amorphous, for example in the case of Portland cement, or it can also be crystalline, such as in the case of calcium aluminate cement. Let us look at the crystallization from melts. We already saw that nucleation is the first phase, then the crystal growth occurs, and then the crystals are bounded by surface defects called grain boundaries. If you see here, this is the structure of crystallization in an alloy of antimony and lead. What we see here is what is called a dendritic structure, a branching structure as the crystals form, and that is shown here. This is the crystal growth along a certain direction, and we see here many of these dendritic structures within. So, the nucleation occurs, then the rest of the dendritic structure starts forming. There is a tendency therefore for the crystal to grow along a preferential direction, which leads to this branched or dendritic structure, and when one dendrite meets another, the growth stops and these points build up, join together to form a polygonal surface or a surface defect, which is called the grain boundary. And finally, after solidification is over, the material now has a granular appearance, as if it is made out of grains stuck together. So, what I have told you now is represented schematically on the right hand side. Initially we have in the melt, as the temperature decreases, nuclei forming. So, there are spots where solidification is initiated. From those points you have growth occurring in this branch manner, that is dendrites start to form. These dendrites keep growing until they meet another dendrite, they have to then stop growing in that direction, the available space fills up and grain boundaries start developing. So, you have these grain boundaries which develop between the crystals or dendrite structures, and that eventually becomes the grain boundary, and you have a grainy appearance to the material consequently. So, first you have the formation of the nuclei, the growth of the dendritic crystals in B and C, then we have the meeting of the dendrites and the slow formation of the grains. Each dendrite has formed from a different nuclei and further crystallized. Finally, you have the grain boundaries forming and giving us a polycrystalline solid. Finally, this is how you have the polycrystalline solid forming. So, these steps are governed a lot by the temperature. First, the melt is at a higher temperature than the melting point. As cooling occurs, we reach the temperature of melting or the melting point. At this point, there is an equal chance for a nucleus to be formed and to be melted. That is, there is as much chance for a nucleus to be absorbed by the melt as to be precipitated. So, at this temperature, solidification really does not start, because the nuclei can be precipitated and as well absorbed. So, nucleation at the melting point is nil or 0. The rate of nucleation increases and goes beyond the rate at which the nuclei are being absorbed by the melt as the temperature is decreased further. That is, the temperature has to be such that the melt is supercooled or undercooled to a critical temperature, T critical. Only below this temperature we have nuclei forming and leading on to the dendritic structure that we talked about before and the grains forming. Suppose you have impurities in the melt, these can act as artificial centers of nucleation called seeds. In the case that seeds are present, crystallization can occur above the critical temperature, T critical, that is closer to the melting point. If it is a pure material, it has to be supercooled to the critical temperature, T critical, but if there are seeds, then crystallization can occur above the critical temperature itself. What we see here on the right is an aluminum ingot about 5 centimeter wide, which shows very clearly the crystallization process. We have on the outside surfaces crystals which are equiaxed, that is, they are having dimensions equal in all directions, almost spherical. This is because cooling would have occurred very fast on the surface. So, crystals are equiaxed when the temperature of the melt is uniform. However, inside there is a gradient of temperature. Innermost we have a higher temperature, outermost you have cooling occurring, so the temperature is lower. So, there is a gradient across the radius of this ingot, and in this direction we see crystals growing from outside towards the center, and we have these radial crystals occurring. So, wherever the temperature is non-uniform, that is, there is a temperature gradient, we have different sizes and shapes of crystals occurring, like we see here. In the center again we have a uniform temperature, and again the crystals can be equiaxed. Schematically, this is what we have just discussed. Now, if I have a mold and molten metal is poured into this mold and the mold is cooled very fast, the temperature drops radially. Outside it is coolest, inside it is almost the temperature of the melt. The temperature of crystallization is reached first at the sides, leading to small equiaxed crystals covering the wall along the sides. Then these crystals grow inward, it is coolest on the outside, so they start there and the crystal grows inward in columnar grains. So, here you see in this section these long grains which form from the outside towards the center. At the center again there is no temperature gradient and we have equiaxed crystals forming. This would be how the temperature gradient looks like, how the temperature distribution looks like. When we talk about crystallization from solution, there also the temperature plays an important role. Crystallization when it occurs from solution is governed by the degree of supersaturation. Only when the solution is supersaturated you have nuclei occurring and the nuclei growing. At saturation the crystal is in equilibrium with the solution, that is the nuclei are dissolving at the same rate that which is causing their formation, that is the rate of dissolution is equal to the rate of crystallization. Temperature changes the level of saturation. At higher temperatures more material can be dissolved, and therefore at a certain temperature you can have a different level of saturation than another temperature. Once the crystal is formed, the rate of growth depends on the diffusion into the growing phases. So, once you have nucleus occurring and then you have a crystal growing, this crystal grows as a function of how much diffusion can occur in the growing phases. Now, we will look at how phase changes occur, and for this we have to again look at what is a phase. We discussed this previously and we said a phase is a homogeneous region within a system in which the properties are uniform. So, you can have a material existing within the total material which has different properties from the rest of the material or other phases. Each phase has a specific composition and atomic structure, and it can consist of one component or multiple components. In this picture of cast iron that we have seen before, we have this cast iron made up of iron and carbon. There is 4% by weight of carbon in this, and there are several phases. The long grey phase that you see here are flakes of graphite which is carbon. The rest, the matrix, is a mixture of iron, BCC iron and iron carbide, which is the rest of the structure. This graphite is a phase which has very different properties from the rest and exists in an identifiable manner. So, in materials we can have different phases occurring. Either the phase is introduced in the fabrication process, or the phases occur when solidification occurs from a melt. In concrete, for example, we have a phase which is the stone phase or the rock phase, which are called the aggregates. These aggregates are mixed into a system which has cement paste, and the aggregates stay without changing their composition through the life of the concrete. So, the aggregates form one phase and the hydrated cement paste forms another phase. In cast iron, the phases form as solidification occurs from the melt. Since the quantity of carbon is very high, this forms a separate phase of graphite within the cast iron. The changes of phases as a function of temperature is governed by phase equilibrium. We see here a simple case of an energy diagram. Here we have on the y axis the energy of the system, x axis we have temperature. This is an energy diagram for two phases, alpha and beta. Say this could be two different packings of atoms in a crystal or two different states of matter, and we have here the energy for alpha as a function of temperature. This is this line. This is how the energy will change as a function of temperature for beta. Now, what we have seen earlier is a material will always choose a structure that provides a lower energy, that is the potential energy or the lattice energy should be lower. So, in this case we see that until this temperature called the transition temperature, beta is stable. After this temperature, alpha becomes stable, because in this region beta requires less energy to form and to stay that way than alpha, but beyond this transition temperature the energy required for alpha is less. So, we say that this would be the stable path and the others are metastable, that is they have to be forced to occur, otherwise the metastable phases will not occur. So, phase alpha has a lower energy than beta at higher temperatures, that is above the transition temperature, and is then the stable phase, whereas beta is stable at lower temperatures and therefore it is the stable phase below the transition temperature. At the transition temperature both energies are equal. The metastable phase will exist only if some energy barrier is there for the nucleation of the stable phase, otherwise it will not occur. Generally the metastable phase will not occur unless there is some reason why the stable phase is not occurring and we are forcing the metastable phase to exist. The metastable phase can be induced to change to the stable phase later by the application of additional energy. This can be mechanical or thermal energy or by the addition of seed crystals, otherwise always it will be the stable phase, because the stable phase requires less energy than the other phase. Now, let us look at when different phases are formed, and for this we have to understand what are solid solutions. Just like we would have solutions in the liquid form, we can have solutions in the solid form. When we have a melt of copper and nickel, we have liquid copper and liquid nickel are completely soluble in each other. So, you have a mix of nickel and copper atoms in the melt. So, when the melt temperature is decreased, we start solidification and a solid copper nickel alloy is formed. In the case of copper and nickel, you have complete solid solubility with copper and nickel atoms occupying random lattice sites that we see here. So, there is a random distribution of nickel and copper atoms within the solid, that means it is a solid solution. However, we have other alloys which do not exhibit complete solubility. For example, in the case of copper and zinc, where the zinc content is more than 30%, we find that instead of having a random distribution of copper and zinc atoms, we have a second phase forming. This phase is a compound of copper and zinc. This separates from the solid solution of copper and zinc and can be identified as a separate phase that is occurring, and this occurs when we have a high content of zinc beyond a certain limit, in this case of 30%. So, even in solids we have a solubility limit, which is the maximum concentration of solute atoms that can dissolve in the solvent to form a solid solution. Beyond this solubility limit, we have a separate phase forming. In the case of zinc and copper, we get this diagram which shows us as the blue line the limit of solubility as a function of temperature. At lower temperatures, we have the limit of solubility of zinc in copper as 30%. At higher temperatures, we can accommodate, we can mix in a little more zinc, reaching about 40% at 400 degrees Celsius. To the left of this curve, we will have a solid solution of zinc in copper, where we will have atoms randomly distributed, both zinc and copper atoms will be randomly distributed within the solid. However, to the right we have one phase which would be the copper zinc compound, another phase would be the solid solution which would have random distribution of copper and zinc atoms. So, this defines the solubility of zinc in copper. The solid line represents, as I said, the solubility limit, and when excess zinc is added, the solubility limit is exceeded, and now two phases coexist. To the left we have only one phase, to the right we have two phases, one the solid solution and the other the copper zinc compound. Now we come to phase diagrams, which you would have studied in the first years of college. There is the interaction of temperature, pressure and composition in a material. The phase diagram is a graphical representation of the combinations of temperature, pressure, composition or other variables for which specific phases exist at equilibrium. In this case we have a generic phase diagram on the screen with pressure on the y axis, temperature on the x axis, and we have different regions where different phases exist. So, the orange is the solid part, that is within this orange area there is the existence of the solid phase, in the purple we have the liquid phase, and in the green we have the gaseous phase. Now we find that between these areas of different colors we have lines where different phases can coexist, that is along this line now we can have the coexistence of both the solid and liquid phase. Here we can have the coexistence of the solid and gaseous phase. Here we have along this line the coexistence of the liquid and gaseous phase. This point, which is called the critical point, is up to where there is a clear definition of the different phases. Beyond this there is no clear definition of the amount of liquid and amount of gaseous phase that can coexist. Between these regions different phenomena can occur, changing the phase from one to the other. For example, here when temperature increases we can have the solid melting to form a liquid. When the temperature drops we can have the liquid freezing to form a solid. Between these two, now the liquid and the gaseous phase, we can have the liquid boiling, vaporizing, evaporating to form a gas, and when temperature drops we can have the gas condensing to form a liquid. We can also have a change in phase from solid to gas and vice versa. When a solid becomes a gas it is called sublimation, where you have the gas occurring without passing through a liquid phase. A gas can become a solid. We use the example of say silica fume, where we said a gas can directly become a solid, fine amorphous solid in the case of silica fume. So, along these lines, as I said, you can have two phases coexisting, but there is always only one point called the triple point where all the three phases can coexist. So, there is only one temperature and pressure couple where all the three phases can coexist, and that is called the triple point. So, let us see some examples of different systems, and before that we will have to define what is called the Gibbs phase rule. The Gibbs phase rule says that if the number of degrees of freedom, now in the previous diagram the degrees of freedom were pressure, temperature, if the number of degrees of freedom are represented by F and the number of phases that coexist by P and the number of components in the system by N, then F plus P is equal to N plus 2. So, this is the Gibbs phase rule. At constant atmospheric pressure, the equation is slightly modified into F plus P equal to n plus 1, F being again the degrees of freedom, P being the number of phases, n being the number of components. So, this is when we take pressure out, that is we assume that pressure is constant, atmospheric pressure, then the Gibbs phase rule is modified as such. As an example, if you have two components, that is n is equal to 2, and a single phase molten alloy, that is P is equal to 1, at constant pressure we would have F equal to 2, n is equal to 2, P is equal to 1. So, F is equal to 2, that is within certain limits both temperature and composition can be varied independently, where the degrees of freedom are now temperature and composition. This can vary independently within a certain limit according to Gibbs phase rule. In the case of a single component system, n is equal to 1, which is water H2O, we get now the Gibbs rule of F plus P is equal to n plus 2 become F plus P is equal to 3. For one phase F is equal to 2, that is if P is equal to 1, F is equal to 2, that is both temperature and pressure can vary. So, if we are looking at only ice, within the limits of ice existing as such, both temperature and pressure can vary. Similarly, for water and for water vapor, the liquid and gaseous phases respectively. But if we want two phases to coexist, that is P is equal to 2, then F becomes 1, right. If P is equal to 2, then F becomes 1, that is only one of the two degrees of freedom can be changed, that is only temperature or pressure can vary independently. The other will be a function of the variable that is changing, that is if you change temperature, for the two phases to coexist there can be only a certain pressure that goes along with that temperature. For three phases to coexist, that is P is equal to 3, F becomes 0, that is you cannot change anything. There is only one point where all the three phases can coexist, that is what we saw earlier and called the triple point. So, the phase diagram for H2O, that is the ice water vapor system, is shown here, where you have now pressure on the y axis, temperature on the x axis, and the different colored regions showing us the different phases that can occur. The light blue is the ice phase, so this is where ice can exist. The dark blue is the water or the liquid phase, and this is the water vapor or the gaseous phase. So, within this you can change both pressure and temperature, where only one phase is existing, that is F is equal to 2, both temperature and pressure can be changed, same within the liquid and within the solid. But if you want to look at when two phases can coexist, we find that it is a line. So, at every point if we change the temperature, there is only a corresponding pressure over which both the phases can exist. So, for ice and water to exist you have to be along this line, there is only 1 degree of freedom. Similarly, for water and water vapor to coexist you have to be along this line, and when you change the temperature there is only a corresponding pressure for which you will be along this line. So, F is equal to 1, there is only 1 degree of freedom. For all the phases to coexist there is only one point where this can occur, there is no degree of freedom, degree F is equal to 0, because this is a constant. This can only occur at 0.006 atmospheric pressure and 0.01 degrees Celsius temperature. So, this gives us how water changes from one state to another, how ice changes to water, water to gas and so on. Similarly, we can have a phase diagram for carbon dioxide. Now again we have this phase diagram where we have pressure on the y axis, temperature on the x axis, all of it is CO2 carbon dioxide. This part is now the solid carbon dioxide, when carbon dioxide can exist as a solid. This is the liquid region and this is the CO2 gaseous vapor region. And as we saw before, within this region both temperature and pressure can change. Carbon dioxide will continue to exist as a solid. Within this region also, that is, you have only one phase. So F is equal to 2, we have 2 degrees of freedom, you can change both temperature and pressure, the liquid CO2 will continue to exist. But when you have both 2 phases occurring, you have to be along this line. In the case of liquid and CO2 gas, solid and liquid along this line, and for all the 3 phases to coexist, it can only occur at this triple point, degree of freedom 0, because it is well defined at 5.11 atmospheric pressure and 216 degrees Kelvin. Okay. What is also interesting from this phase diagram is that there is a range of temperature and pressure where solid carbon dioxide can convert to gaseous form, which includes the normal pressure, that is 1 atmosphere. So at normal pressure 1 atmosphere, carbon dioxide can go from solid form, that is the dry ice form, to directly to gaseous form. That is why it is called dry ice. It does not go from solid to liquid to gas, but directly at normal pressure can go from solid to vapor form. Another single component system which is of interest to us is the system of iron. On the right here you see the phase diagram of iron. At very high temperatures you have iron in the gaseous form. When the temperature at atmospheric pressure is more than 3000 degrees, you have the gaseous form. As temperature decreases, the gas will become a liquid. The liquid will exist at atmospheric pressure up to a temperature of 1535 degrees Celsius. These lines give now the boundaries in terms of temperature and pressure when 2 different phases can coexist, that is, along this line gas and liquid can coexist, and along this line now liquid and the gamma phase of iron can coexist. As the temperature decreases, different phases of solid iron form. This is the gamma phase, which is an FCC structure, the alpha phase, which is a BCC structure, and in some cases when you have very high pressures, you have an epsilon phase, which is a HCP structure. So we find that in equilibrium at normal temperature we have alpha in the BCC form, that is at normal temperatures and pressure, up to 910 degrees you have iron existing in alpha form, that is a BCC structure. When we heat further, when we cross 910 degrees Celsius, we have iron going into the gamma structure, which is an FCC structure. Further heating, there is a small region where a delta structure is formed, which is a BCC structure, and after that the iron completely melts and has a liquid structure. And we saw that there is a case where very high pressures, more than 15 gigapascals, we have a HCP phase and epsilon phase forming. So in this part of lecture 5, we have looked at how different microstructures form. We looked at solidification from melts, starting from nucleation to the dendritic structure and grains forming. And then we have gone on to see how we can describe phase changes through phase diagrams. Until now we have looked at single component systems, we looked at the case of H2O or the ice water vapor system, the CO2 system and the ion system, and we saw what defines or determines when the phases change. In the case of water and CO2, when the solid will become liquid and liquid will become gas and so on. And in the case of ion we saw that there are several solid phases which can occur, which could be the FCC or the HCP structure, and we also saw in which cases different phases can coexist. We looked at Gibbs phase rule which defines when the different phases can coexist, and we looked at examples of the same. Now in the next part of this lecture we look at binary systems, and we will see how we can have binary phase diagrams which again explain to us how there is the interaction between temperature and the composition to define the different phases that can coexist and the types of phases that occur. Thank you.